Very good morning, students.
Good morning, sir.
Morning, sir.
Good morning, sir.
Morning, all of you. Without wasting any time, let us start the discussion. Last class, we have seen about a few methods of preparations of alkyl halides, and in that, Schwarz reaction is a method of preparation for alkyl fluorides. The mechanism for this method is not required, but you have to understand what we are doing. The synthesis of alkyl fluorides is best accomplished by heating an alkyl chloride or bromide in the presence of metallic fluorides such as AgF, Hg2F2, COF2, or SbF3. The alkyl chlorides or bromides, they are heated in the presence of AgF or Hg2F2 or COF2 or SbF3. That is metallic fluorides. That metallic fluorides will be producing F minus greatly. That F minus will be attacking the respective CH3, forming CH3F, and the whatever the chloride or bromide obtained, that will be taken by Ag plus or Hg plus or CO plus 2 or Sb plus ions to form respective precipitates. And this reaction is named as Schwarz reaction. Okay, last class we have seen one more reaction. The name of that reaction is Finkelstein reaction, where we have prepared alkyl iodides. Yes or no? That alkyl iodides preparation is based on difference in the solubilities, whereas this Schwarz reaction preparation is based on the heating of respective alkyl chlorides or bromides in the metallic fluorides. Because of that metallic fluorides, you will get respective F minus substituted, and AgX is going to be lost out as precipitates. Right, students? So these are different reactions for the preparations of alkyl halides. And then you go with the boiling point orders, like properties. Boiling point will depend upon what? Boiling point obviously depends upon molecular weight. Greater the molecular weight, greater will be the boiling point, because of greater the van der Waals force of attraction. Here you can consider 2 points. Boiling point is directly proportional to intermolecular force of attraction. So intermolecular force of attractions are higher when the molecular weight is higher. And molecular weight is whenever the molecular weight is same, then you have to look at branching. Yes or no? So boiling point is also going to be inversely proportional to branching if the molecular weight is same. If the, like if you have alkyl fluorides, alkyl chlorides, alkyl bromides and alkyl iodides, what is the order? CH3F, CH3Cl, CH3Br, CH3I. What is the correct order?
CH3.
CH3IY.
Iodine is largely.
Iodine is going to be CH3I will have more molecular weight, then CH3Br, then CH3Cl, then CH3F. But you can think of the polarity as well. In the other way, if you consider the other way, you can also think of polarity. Like we have carbon fluorine bond here. Carbon fluorine, carbon chlorine, carbon bromine, and carbon iodine bond. So if you think of polarity, CF bond is more polar when compared to CI bond because of more electronegative difference. Because CF bond is more polar, I can develop partial negative on fluorine greatly, partial positive on carbon greatly. Because of this more polarity, more will be the dipole force of attractions or not? Yes or no?
Yes, sir.
Yes.
Because of greater dipole attractions, if you think of that perspective, CH3F should be greater when compared to CH3I. In alkyl fluorides, in alkyl halides, when compared to dipole force of attractions, when compared to dipole force of attraction, van der Waals force are dominant. Right on that point. When compared to dipole forces of attraction, when compared to dipole force of attraction, van der Waals force are dominant. Van der Waals forces are dominant. That is based on molecular weight. We have to decide. That is, we have to decide. We have to decide based on molecular weight. Okay. Example, if you consider CH3, CH2, CH2F, CH3, CH2, like everything is same. Fluorides, chlorides, bromides, iodides will have greater molecular weight. Because of that, you will be having greater van der Waals force of attraction. Because of that, boiling point will be high. Second example, CH3, CH2, CH2, CH2Br, CH3, CH2, CHBr, CH3, CH3, CBr, CH3. What happens with increase in branching?
Increases boiling.
With increase in branching, what happens, students? If you try to increase the
Increasing
branching,
boiling point.
obviously boiling point will be decreasing. So you will have the first compound straight chain will be having greater boiling point, then the uh, branching is less, then the compound where the branching is greater. Why it is so? Because with increase in branching, what happens? The molecule tends to possess spherical shape, thereby decreasing the intramolecular force of attractions. In the third case, what you can say? CH3, CH2, 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 4 carbons are there in the first compound, whereas the second and third compounds has only 3 carbons. So greater molecular weight, greater will be the boiling point. Among these two, branching is deferred. So no branching, high molecular, high boiling point, branching, less molecular, less boiling point. So this is the order. CHBr3, CH2Br, CH3Br, CH3Cl. Based on molecular weight, you can say this is going to be the right order of boiling points. Is that clear or not, students?
Yes, sir.
Yes, sir.
Yes. Okay, due to strong intermolecular force of attraction, boiling point of halogen derivatives is more when we compare them to parent hydrocarbon. When compared to hydrocarbon, halogen derivatives will be having higher boiling points. Why? Because of stronger intermolecular force of attractions. And then the concept of leaving group you have to understand before studying chemical properties. What is leaving group? Leaving group is a species that departs with the bonded pair of electrons. So nucleophile plus Rx. R is an alkyl group connected to some halogen. Nucleophile will try to attack this electrophilic carbon. Like you can look at this alkyl group connected to halogen. The shared electron density is moving towards halogen, developing partial negative on halogen and partial positive on alkyl group. Nucleophile, which is electron rich, it tries to attack the electrophilic carbon. As soon as this attack occurs, the halide ion is lost. That is, the halogen atom has taken these two bond pair of electrons. So the atom which is leaving, taking the bond pair of electron, that is the leaving group. So X minus is the leaving group. And a nucleophile form a new bond with alkyl group. Nu is a nucleophile connected with alkyl group. And X minus is the anion which is produced as the leaving group is lost. Leaving group ability is directly proportional to stability of anion. That is very logical thing. Like if this anion is more stable, then the leaving group is a better leaving group or not? Yes or no? If
Yes, sir.
anion is more stable, like nucleophile attacks the electrophilic carbon, leaving group leaves. If leaving group leaves, you produce anion. If the anion is more stable, then the leaving group is a good leaving group, better leaving group. That means leaving group ability is directly proportional to stability of anion. So weaker bases are good leaving group. Why you can say like this? So acid gives H plus, along with that conjugate base is obtained. If we have weak base means what? Acid will be strong acid. Strong acid will have weaker conjugate base. Strong acid will have weaker conjugate base means, can I also say the conjugate base is more stable? Conjugate base is more stable. That is why it is obtained fastly. Conjugate base should be more stable, then only we can say acid is a stronger acid. If conjugate base is less stable, the dissociation will not happen to produce H plus ion. Conjugate base is more stable, indicates acid is a strong acid. Also, if acid is a strong acid, conjugate base should be weaker base. So, stable conjugate base will be a weaker base. Since it is a stable, it is going to be a good leaving group. Understand this point carefully. Weaker base is obtained from strong acid. Strong acid also indicates conjugate base is more stable. Weaker bases are good leaving groups. Good leaving group means more stable is the respective conjugate base. Okay. Weaker bases are good leaving groups. Why? Because that particular anion is more stable. Why? Because the acid is going to be respect to strong acid. We'll understand with respect to different examples, leaving group tendencies and nucleophilicity. Comparing leaving group ability, like iodine, bromine, chlorine and fluorine are connected to some carbon atom. I minus is lost, Br minus, Cl minus, F minus. Which is a good leaving group?
I minus.
I minus. Why?
Because its size is large
Its
and
size is
in a period.
size is large. The carbon iodine bond, whatever it is there, that is going to be a weaker bond due to poor overlapping. So I minus is a better leaving group than Br minus, then Cl minus, then F minus. Right? Very good. Iodine, bromine, chlorine, they are considered as good leaving groups, whereas fluorine is a poor leaving group. Fluorine is a poor leaving group. Like fluorine OH NR2. Fluorine generates F minus, OH generates OH minus, NH2 generates NH minus, NH2 minus. Like which is going to be the good leaving group now?
Fluorine.
Like negative
Fluorine.
charge on more electronegative atom is more stable, right? So F minus is a better leaving group than OH minus and NH2 minus. So F is a poor leaving group, but OH and NH2 they are very poor leaving groups. OH like Ci, CBr, CCl good leaving groups, CF poor leaving group, COH, CNH2, this OH and this NH2 they will not be leaved easily, because when you try to compare F minus, OH minus, NH2 minus, F minus is more stable. F minus is more stable. Why? Because of more electronegative atom possessing negative charge, right? So OH and NH2 they are even poor leaving groups. Like that you have to compare. Always remember, whenever you are comparing in the period, in a period electronegativity is a dominant factor. I have explained this earlier also. In a period electronegativity is dominant factor, whereas in a group which is a dominant factor?
Size.
Size is dominant factor. Okay. Fluorine, oxygen, nitrogen bearing negative charge. I am comparing electronegativities. So based on electronegativity, we have commented that F is a very good leaving group, like good leaving group when compared to OH and NH2. But if you compare iodine, bromine, chlorine and fluorine, I am comparing size. I am not talking about electronegativity. Okay, in a group, size is the dominant factor. In a period, electronegativity is the dominant factor. N2 plus, OH2 plus. OH is a very poor leaving group. What happened to OH2 plus? OH is a very poor leaving group, but OH2 plus, that is water, is a very good leaving group. N2 plus is also very good leaving group. Yes or no? N2 plus best leaving group. OH2 plus is also good leaving group. When compared to OH2 plus and N2 plus, which is a greater? N2 plus will be greater. Why? Because we'll be having a triple bond between two nitrogen atoms, which will be stabilizing the entropy of the system greatly. If OH2 plus is lost, water is lost. If N2 plus is lost, nitrogen gas is lost. In the nitrogen gas, we have a triple bond between two nitrogen atoms, which actually stabilizes the system greatly. Right? So that is your leaving group tendency for a few examples. Then we have the concept of nucleophilicity. To understand nucleophilicity and compare it, we have to understand solvents first. So substrate plus reagent gives rise to product. This is any organic reaction. And in the organic reaction, we always have a solvent. Solvent is actually two types: polar solvent and non-polar solvent. Polar solvent can again be two types: polar protic, polar aprotic. Okay. There are two types of solvent: polar solvent and non-polar solvent. Polar solvent again classified in two types: polar protic and polar aprotic. Polar solvent can be again classified into polar protic solvent and polar aprotic solvent. Polar protic solvent means what, students?
That solvates both cation and anion.
Very good. We have discussed about this or not earlier?
Yes.
In which reaction we have discussed this?
SN2 and SN1.
Very good. Okay. Polar protic solvent means it solvates both cation and anion. Cation and anion. Polar aprotic means
Only solvent.
cations. Yeah, cations solvated, anions not solvated or free. Nucleophilicity order. Nucleophilicity, which is a better nucleophile, like halide ions, I minus, Br minus, Cl minus, F minus. In polar protic, you decide first.
In polar protic, I minus
Why?
and then Br minus. Because F minus will get solvated due to high charge density.
Very good. Polar protic solvent means due to high charge density, F minus will be greatly solvated. Greatly solvated means F minus surrounded by a very high number of solvent molecules. So it is not going to be a better nucleophile. In polar aprotic means no solvation. No solvation means the F minus, because of high charge density, it will be a better nucleophile, right? Very good. And what about non-polar solvents? Non-polar solvents cannot solvate either cations or anions. Polar solvents like polar protic means both cations and anions are solvated. Polar aprotic means cations are solvated but anions are not solvated. Non-polar solvent means neither cations nor anions are solvated. Okay. Hydrogen atom is directly bonded to electronegative atom. Hydrogen atom is not directly bonded to electronegative. Examples you can take: H2O, partial positively charged hydrogen should be there. Then only we can say polar protic. Partial positively charged hydrogen, wherever it is there, it is called as polar protic. We have partial positively charged hydrogen, partial positive hydrogen, partial positive hydrogen, partial positive hydrogen. In other cases, N comma N dimethyl acetamide, CH3, C double bond O, N CH3, CH3. So there is no partial positive hydrogen. N comma N dimethyl formamide, DMF, HC double bond O, N CH3, CH3. Acetone, no partial positive hydrogen. DMSO, dimethyl sulfoxide, CH3, S double bond O, CH3, no partial positive charge hydrogen. Ether, ROR. Ether is polar or non-polar? Ether is polar. You have to understand ether as a polar. You should not look at this ROR in a straight line. Because of the presence of lone pair of electrons and oxygen, ether will actually exist in a bent shape. So it has some polarity. It is polar, but it is aprotic solvent. Polar aprotic. Okay. Both cations and anions are solvated in a polar protic. In a polar protic solvent, like Na plus NaCl, if you add to H2O, Na plus ion is solvated, Cl minus is also solvated. Non-polar solvent, neither cation nor anion is solvated. Non-polar solvents, you can say CCl4, CS2, etc. Only cations are solvated and not anions. This is due to steric crowding, where in polar aprotic, like acetone, DMSO, DMF, yes or no? So acetone you have taken polar aprotic solvent, only cations are solvated, not anions. And non-polar solvent means neither cation nor anion is solvated. That is CCl4, CS2, etc. Is that clear, students?
Yes.
Yes, right. So this is the difference between polar protic, polar aprotic. So nucleophilicity means what? Now comes the concept of nucleophilicity. Nucleophilicity is the measure of how fast, understand this point, how fast a nucleophile is able to attack an electrophilic center. It is a kinetic property. Always we are writing a reaction has been written. We do some rearrangements. If it is a carbocation as the intermediate, ring expansions, or if 4-membered ring is the intermediate, we do the look at stabilities. If 3-membered cyclic ring is the intermediate, we look at stabilities. We do some stabilities. We do some rearrangements, or based on 4-membered or 3-membered ring stabilities, we ultimately write the respective major product. But always think of other perspective. Is that major product obtained fastly? There are two cases always. One is the thermodynamically controlled reaction, other is a kinetically controlled reaction. Whatever the major product we are arguing, we say major product, major product, major product. But is that major product obtained fastly? No. The major product may or may not obtain fastly in the reaction mixture. The kinetic product, there is a kinetically controlled product, there is a thermodynamically controlled product. The thermodynamically controlled product is a major product. That thermodynamically controlled product can be obtained fastly or it takes some time. Okay, kinetically controlled product is obviously the fastly obtained product. It may be major or it may not be major. There are some set of reactions. You will understand about the thermodynamical controllability and kinetic controllability in the higher standards. But what is nucleophilicity means? Nucleophilicity is the measure of how fast a nucleophile is able to attack. How fast? Understand this term, how fast. That means it's a kinetic property. If you think of basicity, basicity is not about how fast it is attacking. Basicity is about the stability. Basicity is a thermodynamic property. It relates with stability. It is not about how fast you did attack the proton. It's about if it attacks, it will be stabilized greatly or not. Nucleophilicity refers to how fast a nucleophile can attack the electrophilic center. It is a kinetic property, whereas basicity is a thermodynamic property. F minus, Cl minus, Br minus, I minus. So if you talk of bases like HF, HCl, HBr, HI you take. HF, HCl, HBr, HI, all of them produces H plus ions. Along with that, they will produce F minus, Cl minus, Br minus, and I minus. Which is more acidic? HI is more acidic because of large size of iodine when compared to hydrogen. So poor bond, so that can be broken easily. HI more acidic means what happened to I minus? Is a weak base or not? I minus is more stabilized, that is okay. But what about strength? It is a weak base. So respect to I minus is going to be more stable. More stable anion means weak base. Understand this logics. Stable anion, HI is a strong acid. Why? Because the hydrogen and iodine has poor overlapping because of large size difference. So that bond can be broken easily, generating H plus and I minus ion. HI is a strong acid means I minus should be more stable. I minus is a more stable anion. HI is a more strong acid means the respective conjugate base should be weak. So stable anion means weak base. Try to compare F minus, Cl minus, Br minus, I minus. Which is a strong base? HF weak acid. F minus will be a strong base. So what is the order of basic nature? F minus, Cl minus, Br minus, I minus. So F minus, Cl minus, Br minus, I minus basic nature order will be this one. Okay. Order of basic nature. Okay, understand this point. The nucleophilicity and the basicity order in a period is almost same. The nucleophilicity and basicity have same order in a period, whereas in a group, the nucleophilicity and basicity may or may not have same order. We'll discuss that points. And in a group, if you are trying to compare nucleophilicity order and basicity order, that depends upon solvent. If you want to compare the order of nucleophilicity with the order of basicity in a group, solvent comes into picture. This is the order of basicity. This is the order of basicity, F minus, then Cl minus, then Br minus, then I minus. What is the order of nucleophilicity? F minus, Cl minus, Br minus, I minus, order of nucleophilicity. That depends on solvent or not? F minus greater than Br minus, greater than Br minus, greater than I minus. I minus greater than Br minus, greater than Cl minus, greater than F minus. This is in polar aprotic solvent. First one. Whereas second one is polar protic solvent. What are these? This is nothing but order of nucleophilicity. So the order of nucleophilicity in the polar aprotic solvent and the order of basicity, are they same?
Yes.
This is order of basicity. Order of basicity. Order of basicity and order of nucleophilicity in polar aprotic solvents, they are same. Order of basicity and order of nucleophilicity in polar aprotic solvents, they are different. Whenever you are looking in a group like fluorine, chlorine, bromine, iodine, they are in a group, right? Whenever you are comparing in a group, the order of nucleophilicity and order of basicity, they may be same, they may not be same. That depends upon solvent. Like here, if polar aprotic solvent we have taken, order of basicity and order of nucleophilicity are same. Polar protic solvent, if you take, order of basicity and order of nucleophilicity are different. But if you consider in a period, the order of nucleophilicity and order of basicity are same. Okay?
Yes.
Right? Very good. Factors affecting nucleophilicity. First point, a negatively charged nucleophile is a better nucleophile than its conjugate acid, obviously. If a particular species already has negative charge and other species which is neutral, it may have lone pair of electron to donate, but one species has negative charge. A negatively charged nucleophile is a better nucleophile always when compared to neutral species. RO minus ROH. ROH is also acting as nucleophile because of lone pair of electrons on oxygen, but RO minus is a better nucleophile. NH2 minus NH3. NH3 can also act as a nucleophile because of lone pair present on nitrogen, but NH2 minus is a better nucleophile because of negative charge. OH minus H2O. OH minus is a better nucleophile. That is, a negatively charged nucleophile is a better nucleophile than its respective conjugate acid. That is the first point which you can understand easily. Second point, when the attacking nucleophile is approximately same in size, that means in a period we are talking about, then a stronger base is a better nucleophile. That means order of basicity and order of nucleophilicity is same in a period. Order of basicity and order of nucleophilicity is same in a period, but may or may not be same in a group. And it depends on solvent. Yeah, this is what across a period nucleophilicity and basicity order is same. CH3 minus NH2 minus OH minus F minus, which is a better nucleophile or better base, because order of basicity and order of nucleophilicity is same. Negative charge and more electronegative atom is more stable. Compare here, students, which is a better nucleophile or better base, stronger base. CH3
F minus.
better base, I am asking. Think carefully, all of you. CH3 minus NH2 minus OH minus F minus. Which is more stable? You compare the order of stability first. Which is more stable?
F minus.
F minus is more stable. More stable means weak base or strong base?
Weak base.
Weak base. So F minus is weak base, no? Yes or no? Like HF, you always consider HF gives H plus and F minus. HF is a weak acid. Weak acid means strong base. Strong base also means weak acid means respect to strong base. Strong base also means F minus is more stable or less stable?
More stable.
More
More stable.
HF is a weak acid. HF is a weak acid means whatever the conjugate ion we are obtaining, that should be less stable. With respect to HF, you comment first. HF gives H plus and F minus. HF is a weak acid. If you compare HF, HCl, HBr, HI. HF is giving H plus and F minus. HF is a weak acid means whatever the F minus you are obtaining, that is going to be, HF is a weak acid means F minus is going to be strong base. HF is a weak acid means F minus is going to be unstable. Yes or no? Weak base means unstable anion. This is in the comparison of HF, HCl, HBr, HI. When you are comparing CH3 minus, NH2 minus, OH minus, F minus, negative charge on more electronegative atom is more stable. So more stable means a weakest base. So F minus is more stable when you try to compare among these three, like a CH3 minus, NH2 minus, OH minus, F minus. F minus is more stable when you compare with CH3 minus, NH2 minus, OH minus. You understand this? When you compare HF, HCl, HBr, HI, F minus is unstable. Okay, with respect to what you are comparing, that is important. F minus is more stable among these four, so that is going to be the weakest base. CHC minus is going to be the strongest base. The order of basicity, and that is the same order of nucleophilicity. Right? Is that clear, students?
Yes.
Yes, right. So when the attacking nucleophile is different in size in a group, when an attacking nucleophile is different in size in a group, then role of solvent you have to take into account. Like polar protic solvent means, what is the order? I minus greater than Br minus greater than Cl minus greater than F minus. So polar protic solvent means I minus is a better nucleophile, and basicity order F minus, Cl minus, Br minus, I minus. So the order of basicity and order of nucleophilicity, they are going to be different when the solvent is polar protic solvent. Order of basicity and order of nucleophilicity are same when the solvent is polar aprotic solvent. Polar aprotic solvent means F minus, Cl minus, Br minus, I minus, no solvation of anion. Basicity order is also F minus, Cl minus, Br minus, I minus. The basicity order and nucleophilicity order in polar aprotic solvent are same. Basicity order and nucleophilicity order in polar protic solvent are different. They are opposite. Is that clear, students?
Yes, sir.
Yes. And if they have not mentioned anything, solvent they have not mentioned, then which solvent you have to consider? If they are not mentioned any solvent, you have to consider as a universal solvent or polar protic solvent only. You should not consider polar aprotic solvent if they are not mentioned. Okay, if nothing is mentioned, you have to consider polar protic solvent only. Next, in a group, in a period, we have compared, and negative charge we have compared. In case of same donor atom, if the donor atom is same, generally nucleophilicity and basicity order is also same. If you have same donor atom, nucleophilicity and basicity, they have same order. Stronger base is stronger nucleophile. You have to compare basicity and apply the same to nucleophilicity. In the case of same donor atom, basicity and nucleophilicity is same. Compare here OR minus, PHO minus, RC double bond O minus H2O. OR minus is obtained from ROH. PHO minus obtained from PHOH. RC double bond O minus obtained from RC double bond OH. Which is a stronger acid?
RC double bond OH.
RC double bond OH is a stronger acid. Why? Because of equivalent resonating structures. RC double bond OH is a stronger acid. So stronger acid means respect to RC double bond O minus is going to be a weaker base. ROH is a weaker acid. So RO minus is a stronger base. Donor atom is same. Oxygen, oxygen, oxygen. Same donor atom means order of basicity. OR minus is a strong base, then PHO minus, then RC double bond O minus is the weakest base because respect to acid is strong. And after these three, I'll be considering H2O. Why? Because the first three are nucleophiles, where nucleophiles with a negatively charged species. First three are negatively charged nucleophiles, whereas water is a neutral one. When compared to neutral, negatively charged centers are going to be more nucleophilic. So RO minus, then PHO minus, then RC double bond O minus, then H2O. This is the order of nucleophilicity. Order of nucleophilicity. List down all the factors or rules, students. Rule number 1, negatively charged species are more nucleophilic when compared to respect to conjugate acids. Rule number 2, in a period, order of basicity and order of nucleophilicity is same. So you have to just compare the basicity order, apply the same to nucleophilicity order. In a group, order of basicity and order of nucleophilicity, they may be same or different. You have to take the role of solvent into effect. Role of solvent into consideration. So if you consider basicity and nucleophilicity in polar aprotic, they are going to be same. Basicity and nucleophilicity in polar protic, they are going to be different. And in last rule, in the case of same nucleophilic atom, basicity and nucleophilicity order again same. That is similar to period. Stronger nucleophile is a stronger base. Based on that, you have to compare compare the order of basicity by looking at respect to conjugate acids? Yes or no? Acid base comparison you can do. And negatively charged nucleophile is great nucleophilic when compared to neutral nucleophile. So this is the order of nucleophilicity, right? So after this, leaving group tendencies, solvents, and nucleophilicities, we are good to start with the chemical reactions of haloalkanes. The reactions of haloalkanes may be divided into following categories. We have nucleophilic substitution reactions. In the nucleophilic substitution reaction, what type of reaction we have discussed earlier? SN1, SN2, SNI. Elimination reactions, E1 and E2. And reactions with metals, some formation of Grignard agents and all. Okay. Woods reaction, Grignard reagent. Okay, these are the reactions which you are going to see. Nucleophilic substitution reaction, nucleophile is going to be substituting. That means the halogen, whatever it is there, that is going to be lost as halide ion, and nucleophile will be substituting that particular position. This reaction has been found to proceed by two different mechanisms, that is SN1 and SN2 mechanism. SNI is there with respect to SOCl2. That is not directly given as in your NCRT, that's why not given here. SNI, you have to understand the details. We have explained with thionyl chloride and all. But as per your syllabus, only SN1 and SN2 are there. SN1 is 1 stands for unimolecular, N stands for nucleophilic substitution. Unimolecular nucleophilic substitution is SN1. SN2 is bimolecular nucleophilic substitution. Let us start with one by one, students. Unimolecular nucleophilic substitution reaction. Okay, unimolecular nucleophilic substitution reaction or SN1 reaction. I'll ask the question since the mechanism is already discussed. In how many steps this reaction happens?
3 steps.
3 steps, Faizan.
2 steps.
More than
In how many steps this SN1 reaction occurs? It occurs in 2 steps. What is the step 1?
Formation of carbocation.
Carbocation. What is step 2?
Attacking of nucleophile.
Attacking of nucleophile. Carbocation is formed. So realignment is possible or not? Obviously
Possible.
possible. What is the order of this particular reaction?
1.
tertiary, that is one
Order is going to be unimolecular because the first step is the rate determining step. Formation of a carbocation is rate determining step. So rate of the reaction directly proportional to only concentration of substrates. Order is going to be 1. Molecularity is also 1. What type of solvents are preferred in this reaction? Polar protic or polar aprotic?
Polar
polar
protic.
Polar protic. Why?
Because rate does not depend upon nucleophility.
Because the polar protic solvent, they are going to help in actually ionizing the bond. Yes or no? The carbon chlorine bond or the carbon halogen bond is there, right? Carbon halogen bond. This carbon has partial positive, this halogen has partial negative. Let us say it is connected with 3 other groups, R1, R2, R3. And we have a polar protic solvent like water. The water will develop electrostatic force of attraction with a partial positively charged carbon. And they will also develop electrostatic force of attraction with partial negatively charged halogen. Because of this new attraction, the carbon halogen bond is going to be cleaved easily. Yes or no? The carbon halogen bond can be cleaved easily in the presence of polar protic solvent, or I can say polar protic solvents are helping in ionizing the bond. You cannot say they stabilize the carbocation only, because the carbocation, whatever is formed, it is a cation. Cations are solvated both in polar protic as well as polar aprotic. The main difference is the polar aprotic are actually stabilizing, or they are used in ionizing the carbon halogen bond, which is the first step. Yes or no? The breaking of CX bond to form a carbocation is a step 1, which is a rate determining step. Polar protic solvents are used. And what is the order? Tertiary alkyl halide, secondary alkyl halide, primary alkyl halide. tertiary, then secondary, then primary because of stability of carbocation. Why 3-degree carbocation is more stable? More number of hyperconjugated structures. Yes or no? And what is if we have a good leaving group, obviously the rate of SN1 will be high. So these are the same points which you are going to see again. So mechanism step 1, Rx converting into respect to R plus and X minus. It is going to be slow, RDS. The carbocation attacked by nucleophile fastly to form RNU, which is the product. Characteristics, it is a two-step reaction. Kinetics of the reaction, rate is directly proportional to concentration of alkyl halide. Proportionality have removed, so you can insert a constant which is nothing but rate constant. So order of this reaction is 1, molecularity is also 1. Rate of reaction is directly proportional to concentration of alkyl halide only. That means it is independent of the concentration of nucleophile. That means it doesn't matter whatever the nucleophile you have taken, how strong a nucleophile is or how weak a nucleophile is, it doesn't matter. If it is SN1 reaction, it will not depend upon the concentration of the nucleophile. It only depends upon the concentration of alkyl halide. Rate is independent of concentration of nucleophile. Carbocation intermediate is formed, so rearrangements may be possible. SN1 reaction is favored by polar protic solvents, example water and alcohol. Why? Because polar protic solvents helps in ionizing the bond and also helps in stabilizing of charges. Okay, the bond which is there, Rx bond, that has to be cleaved to produce R plus and X minus in the rate determining step. So that bond cleavage is going to be helped. That cleavage of bond is actually helped by the polar protic solvent, not aprotic solvent. Right? Is that clear, students?
Yes, sir.
Yes, sir.
Yes. Stereochemistry, who can answer? SN1 reaction stereochemistry. What happens? Racemization or inversion or partial racemization or retention?
Partial racemization.
Partial racemization occurs. If partial racemization is not given in the options, then you can go with the racemization. But exactly partial racemization occurs. Why partial racemization? Because the leaving group, whatever is obtained, it is not diffused greatly. So we have R dash, CX, CR, CR double dash, converting into R dash, C plus, R dash, R double dash. sp3 hybridized carbon converted to sp2 hybridized carbon. Here we have sp3, here we have sp2. We can think of attack of nucleophile from the top as well as from the bottom. But the opposite attack is great because the leaving group has not diffused greatly. We can get retention product and inversion product. In the inversion product, nucleophile occupies a position opposite to that of leaving group. Okay. Theoretically, recipe mixture must be formed. If you go with the theory, recipe mixture must be formed, but inversion products dominates over retention products. Why? Because the leaving group has not diffused. Because leaving group didn't diffused away. Reactivity towards SN1 reaction is directly proportional to stability of carbohydrate intermediates. Primary, secondary, tertiary, allyl benzyl if you take, which will be more stable carbocation?
Tertiary.
Tertiary, benzyl, allyl, secondary, and then primary.
Tertiary, benzyl, allyl, secondary and primary. This was the exception case. Why tertiary is more stable? Only tertiary butyl. Okay, this tertiary means only tertiary butyl. That is CH3C plus CH3C CH3. You cannot consider any tertiary. Okay, only tertiary butyl, because if I consider any other tertiary like C2H5, C, C2H5, C, C2H5, in that case, number of hyperconjugated structures differ or not? Yes or no?
Yes.
Only tertiary butyl if you consider, then it will be having greater stability that is explained based on rates of hydrolysis. So tertiary is greater than benzyl, then allyl, then secondary, then primary. If the leaving group is different, then better leaving group, grade will be rate RI, RBr, RCl, RF. That will be the correct order. SN1 reaction does not take place in which systems? Aryl halide, vinyl halide. Why? Because
Because
carbocations are unstable. In vinyl halide, vinyl carbocatane is unstable. In aryl halide, why it will not form? Many reasons are there. One reason is aryl carbocatane is
Double bond
unstable.
character.
Carbon halogen bond, double bond character, very good. Any other reason? Carbon is sp2 hybridized carbon. The sp2 hybridized carbon is more electronegative when compared to sp3 hybridized carbon. So the carbon halogen bond is less polar. Can I say like that? When you compare this carbon sp3 hybridized connected to halogen, carbon sp2 hybridized connected to halogen. Halogen, let us say halogen is fluorine, which has electronegativity of 4. Here also 4. Carbon sp3 hybridized carbon has an electronegativity of how much? 2.5. sp2 2.75. What is the difference in electronegativity? 1.5 here, 1.25 here. So where the difference in electronegativity is high? In the CX bond where carbon is sp3 hybridized, but in the CX bond where carbon is sp2 hybridized, the difference in electronegativity is less. Because of less difference in electronegativity, the bond is less polar, so nucleophile cannot attack easily. Vinyl halide, aryl halide, no SN1 possible. SN2 is also not possible for vinyl and aryl. Vinyl and aryl, SN2 is also not possible due to steric repulsions. And this compound is violating the Brett's rule, so Brett's rule violated, so SN1 does not take place. Compare here, students, compare rate towards SN1 reaction. A, B, C, D, 4 have been given to you.
DC.
DCB.
D, C, B, A. In D, we have tertiary carbocatane. In C, we have secondary. In B, we have primary. In A, we have methyl. So based on number of hyperconjugated structures, we have explained this. Here you try to compare. Here the respective carbocations formed are these. The benzylic carbocations are formed. And we are converting it NO2, CH3, OCH3, NH2, which is a beta electron donating group.
DCB.
Electron donating group decrease the charge, thereby increasing stability. So D is a better electron donating group because which group is this? Plus M. OCH3 plus M. CH3 what type of group? Plus
Plus
H.
H.
Minus M is NO2. So D, C, B, A. When compared to D and C, how we have compared? NH2 is greater. Because nitrogen is less electronegative, right? Less electronegative nitrogen cannot withhold the lone pair greatly. It will be used in the donation greatly. So DCBA, that is the right order. Compare here.
DBAC.
Sorry, Faizan, what is the order?
DBAC.
DBAC. So here you are getting a benzylic carbocatane. Here you are getting tertiary butyl carbocatane. Here you are getting allylic carbocatane. Here you are getting carbocatane in this manner. So D is actually stabilized by back bonding or not? And you have in the compound D, if you try to write the resonating structure, the resonating structure will have complete octet for all the atoms. Because of that, D is ultimately stable. Then tertiary butyl carbocatane, benzylic allylic. So after D, you have B, B after that A after that C. This is the right order. Very good. Compare rate here, rate towards SN1 reaction. These are the respective
ABC.
carbocations. Yes.
ABC.
Why C is least?
Non-aromatic, anti-aromatic nature.
Anti-aromatic in nature. Okay. In C, we have anti-aromatic nature. In A and B, A is aromatic in nature. B is just a secondary carbocatane. A is more stable than B, then C. A is aromatic, B is secondary carbocatane stabilized by hyperconjugated structures. Anti-aromatic is highly unstable. So A greater than B greater than C, that is the right order towards SN1 reaction. Very good. So then comes the bimolecular nucleophilic substitution reaction. In bimolecular nucleophilic substitution, we have the same reaction. In how many steps the reaction occurs?
Single step.
Single step reaction. Bimolecular nucleophilic substitution is a one-step reaction. Nucleophile attacks the electrophilic carbon. Leaving group leaves. This is happening simultaneously. So RNU plus X minus obtained. So what is the characteristic? So what is the transition state here?
Inversion of
5-member transition state.
5-membered. 5-membered means ring. Like penta coordinated transition state is obtained. Like the electrophilic carbon is actually surrounded by 5 groups which are about to form bonds and about to leave bonds, and 3 bonds are real. It's a single step reaction. So rate depends upon both concentration of nucleophile and concentration of alkyl halide. So rate of a reaction should be directly proportional to concentration of alkyl halide and nucleophile. So order will be 2 and molecularity is also 2, because in the rate determining step, only one step, that is the rate determining step. So 2 species are there. So molecularity 2, and rate depends on both of them concentration. So order is also 2. Rate is depending on concentration of nucleophile. So stronger the nucleophile, greater will be the rate of SN2 reaction. No carbocation intermediate is formed, so no rearrangements. SN2 reaction is favored by polar aprotic solvent. Why? Because in polar protic solvent, that polar protic solvent is helping to ionize the bond. If the bond is ionized, we get a carbocation. If you take a polar aprotic solvent, that is not helping to ionize the bond. Okay. So SN2 reaction, that is why is favored by polar aprotic solvent like DMSO, dimethyl sulfoxide, dimethyl formamide, acetone, etc. Stereochemistry of SN2, what happens? Walden inversion occurs. Complete inversion occurs, 100% inversion product. OH minus attacks the carbon, Cl leaves. It is nothing but a penta coordinated transition state. Yes or no? This symbol indicates transition state. OHC, carbon connected to alkyl group, deuterium and hydrogen, and Cl minus lost. Yes or no? So transition state is penta coordinated, and inversion of configuration or Walden inversion occurs. Stereochemistry of SN2 means, so SN2 reaction completes with 100% inversion of configuration. So whatever the nucleophile we have to place that nucleophile exactly opposite to that of leaving group. So 100% inversion is going to happen. So trick is to create inversion product in wedge dash, draw mirror image and replace leaving group by nucleophile. Okay, you know how to draw mirror image, right? You keep it mirror. Draw a mirror image, chlorine will be here, carbon, alkyl group as it is, deuterium in this fashion and hydrogen in this fashion. Now chlorine is the leaving group, that you have to replace with OH. This is how the animation looks like. OH minus can never attack from the same side, and it will attack from the back side, about to form, about to broken, and those bonds are going to be cleaved now. And as soon as the bonds cleaves, you get a respective inverted product. Is that clear, students?
Yes.
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 Yes, right. Very good. So OH minus CH3C CDCH. What you are going to do? OH minus you have to place at the position of OH minus you have to place at the position of CCl, right? So here it should be OH, because chlorine is going to be a leaving group, and you have inversion happening. So you have to write the mirror image and just to place OH wherever you have the leaving group earlier. Just to draw the mirror image and replace the leaving group with the nucleophile, and that's what the animation is showing. And we have seen the RS nomenclature also. If you try to figure out the RS nomenclature, that will be reversed. right? What happens here? OH minus attacking this particular carbon, OH minus will be towards our side or to away from our side. Leaving group, check out the stereochemistry of leaving group. Chlorine is towards the observer, so OH minus has to be away from the observer, because nucleophile and leaving group, they have to be configuration exactly opposite. Leaving group wedge means nucleophile should be dash. Leaving group dash means nucleophile should be wedge. So this is the Fisher position given to you. So OH minus is now going to attack, and you will be leaving the bromine. So the where the OH should be substituted? To create inversion product in Fisher projection, replace leaving group by nucleophile and exchange one pair. Here nucleophile you have to replace with the bromine. Here replacement is not done, so you have to replace it. OH you have to place it, and after placing OH you have to exchange one pair. Like if I simply replace bromine and add OH here, that is not having the inversion product. But if you exchange one pair, then you can say CH3DOHH. This is nothing but the correct product. Because inversion or exchange of only one pair will invert the product or not. As I have told you in the rules of exchanges, if you try to do multiple number of exchanges or even number of exchanges will be having the same configuration. If you do exchange only one times, what happens? The configuration will be reverse. So if you want to create the inversion product in Fisher projection, replace leaving group by nucleophile. Bromine I have replaced with OH, and then I have done the exchange of one pair. OH and H I have exchanged. Is that clear, students?
Yes.
These
sir.
Yes.
okay, these exchange rules has a great significance whenever we are talking to trying to assign RS nomenclature in the wedge dash for 3D molecules. Yes or no? Like you will be assigning CIP rules like 1, 2, 3, 4. So in that always the fourth priority group should be on the dash line. So to attain that, you will do the exchanges. Reactivity towards SN2 reaction. Inversely proportional to steric hindrance. If you take primary, secondary, and tertiary, which will be more reactive?
Primary.
Primary.
Inversely proportional to steric hindrance, directly proportional to electrophilicity of carbon attached to halogen. So CH3X, methyl halide, primary, secondary, and tertiary. Methyl halide will be greater than primary, then secondary, and then least is going to be tertiary. Check degree first. If degree is same, check electrophilicity for primary. Like first you have to check whether primary, secondary, or tertiary taken. Primary, secondary, tertiary, three different are given to you, then primary greater, then secondary, then tertiary. If two compounds given to you are both primary, then you have to check out electrophilicity. Like I will be giving this compound CH3, CH2X, CH3, CH3, CH2X. Here I'll write CH3, CH2X, CH3, CH2, CH2X, CH3. Here you can write CH3, CH2, CH2, CH2X, and CH3, CH, CH3, CH2X. Out of these two, which is more reactive towards SN2?
First.
First compound will be more reactive because the carbon halogen bond is going to be polar, generating partial positive here, partial negative here. The partial positive charge is nullified by only one carbon-carbon bond. But here you have two methyl groups, both are electron donating. They will donate the electron density greatly, decreasing the positive charge greatly. So if degree is same, if we have same primary alkyl halides, then you have to check the electrophilicity. So less electrophilic means less reactive, more electrophilic means more reactive. For steric hindrance, like you have to check steric hindrance for secondary and tertiary. If secondary and tertiary are given, you have to check the steric hindrance. Right? Primary, all these three are primary. So which will be great? Yes or no? Based on this, based on the electrophilicity of carbon, you can comment. The first compound is going to undergo SN2 greatly, and you can also say less steric repulsion is also there. Yes or no? This primary is going to be having greater SN2 than the other one, Then the last one, because electrophilicity of the carbon has been differed. Here more electrophilicity and lesser steric repulsions. Everyone got the students? Yes or no? Assign to orders.
Yes, sir.
Yes, sir.
Branching at beta position. This is alpha, this is beta. Branching at beta position decreases rate of SN2 because of increasing steric repulsions. Allyl and benzyl halides show SN2 reaction in good amount. Why? Allyl and benzyl. If you take CH2 double bond CH CH2X and benzyl C6H5 CH2X, they show SN2 in a good amount. That means rate of allyl and benzyl is greater than rate of CH3X towards SN2. If you talk of SN2 reaction, if you take methyl halide due to very less steric repulsions, they are going to have SN2 greatly. But here we are saying allyl and benzyl halide show SN2 greatly in good amount. And if you compare that, the rate of allyl and benzyl will be greater when compared to CH3X. What was the reason? Look at the reaction. Okay, this is a partial positive charge carbon, this is a partial negatively charged halogen, partial positive charge carbon, partial negatively charged halogen. Because of partial positive charge present on this carbon-carbon bonds, they are going to be in resonance or not? Resonance possible or not? Here also resonance possible. But now think of this attack. Nucleophile is about to attack this particular carbon. This carbon is allylic halide I am talking. This carbon is about to leave a bond. This CX bond is about to cleave. And we have two hydrogens connected to that particular carbon. And we have carbon is connected to CH double bond CH2. CH double bond CH2. This carbon has partial positive charge. And same benzyl you consider, students. Benzyl. Nucleophile is trying to connect a new bond with this carbon. Carbon has two CH bonds. Carbon is also connected with halogen. That bond is about to leave. And that carbon is actually connected to a phenyl ring. And this carbon has partial positive charge. This is a scenario or not? This is the penta-coordinated transition states obtained or not? Yes or no?
Yes, sir.
Now you ask the same questions, whatever I'm asking. You answer the same questions, whatever I'm asking. Like if the positive charge is great, the resonance will be great or less. Like here we have allyl halide. No. The carbon is connected with halogen. On the carbon, if positive charge is high, the resonance will be high or less?
High.
High, obviously, because pi electron density resonance with the positive charge. Nucleophile is now about to form a new bond with the positive charge. So positive charge is decreased or increased?
Decreased.
Positive charge is decreased. Positive charge is decreased means what happened to this carbon-carbon double bond resonance? Increased or decreased?
Decreased.
Decreased. So if resonance is decreased, then can I say the carbon-carbon double bond is stabilized? Because that pi electron density is now localized, not delocalized. Understanding
Yes,
this point
sir.
or not? Simple logic. The nucleophile is about to attack a carbon. The carbon has partial positive charge. Since the nucleophile is attacking the carbon, the partial positive charge in that carbon is decreased. Because of the decrease in partial positive charge, the carbon which bears a positive charge, which is connected to phenyl ring, whatever the three pi bonds we have, they are stabilized. Okay? As a nucleophile reducing the partial positive charge, it will actually stabilize. It will actually stabilize the carbon-carbon double bond. CC double bond, and thus having greater rate. Okay. So now you compare among allyl and benzyl. In benzyl, 3 pi bonds are stabilized. In allyl, only 1 pi bond is stabilized. So benzyl will be greater when compared to allyl. In allyl, there was resonance, but only with respect to 1 pi bond. But that resonance is stopped. So pi bond has been stabilized. The pi electron density is not moving away. But in benzyl, you have 3 pi bonds. The 3 pi bonds are not going into resonance. So 3 pi bonds are stabilized. So greater stabilization happened in benzyl when compared to allyl. So benzyl is going to be more stable or having greater rate towards SN2 when compared to allyl. Understood this point, everyone?
Yes, sir.
Yes, right. And now CH3 C double bond of CH2X shows SN2 in excellent amount when compared to benzyl and allyl. This will have excellent amount. Why? Because nucleophile is now going to attack this particular carbon, which is connected to 2 hydrogens, and that carbon is also connected to halogen, which is about to cleave, and this carbon is connected to C double bond O. It is connected to CH3. Because of reduction in partial positive charge, the C double bond O is stabilized or not? Here, because of nucleophile attacking partial positive charge, partial positively charged carbon, the C double bond O group is stabilized. The C double bond O is stabilized. The C double bond O is a stronger bond when compared to C double bond C. So here C double bond O is stabilized. Because of that, it will have excellent rate. Rate towards SN2 will be CH3 C double bond O CH2X, that will be having highest. Then you have benzyl, and then you have allyl. Okay. CH3 C double bond O CH2X will be having greater rate towards SN2. You should not say that, sir, here we have C double bond O CH3, so bulkiness is very high, so nucleophile cannot attack. No, it can attack. Why? Because of the attack of nucleophile, the C double bond O is stabilized. Because of stabilizing C double bond O, C double bond is a stronger bond. If you are stabilizing a stronger bond, that will be having greater rate towards SN2. Right, student? These were interesting things to note. And SN2 reaction does not express in vinyl halide, no SN2, aryl halide, no SN2, and also bread stool. Wherever bread stool is violated, there also no SN2. Tertiary alkyl halide, neopentyl halide, and bread stool violated in last case. Here, what I can say? Bread stool and steric repulsions. You may ask a question, sir, how we can say bread stool? The carbocation is not obtained, but look at the steric repulsions. And also this carbon develops some partial positive charge or not? It is not a carbocation, but resembles a carbocation to some extent. Neopentyl halide, because of very high steric repulsions. Tertiary alkyl halide, more steric repulsions. Here, more steric repulsions. When compared to tertiary alkyl halide, neopentyl halide will be great. When you try to compare, but both of them will not have any SN2. So SN1 and SN2 reaction does not take place at sp2 hybridized carbon, that is vinyl or aryl or bicyclic systems, like where bread stool has been seen to be violated. Is everything clear, students, with respect to SN1 and SN2?
Yes,
Yes,
sir.
sir.
Right. Compare the rate towards SN2 reaction. ABCD. Very simple.
ABCD.
A, B, C, and D, because methyl primary, secondary, tertiary. This is methyl. Compare the rate towards SN2. Allyl, benzyl, aryl, and primary. So benzyl greater, then allyl, then primary, and least is going to be aryl. SN2, SN like tertiary alkyl halide, secondary alkyl halide, primary alkyl, if you compare, primary alkyl halide and secondary alkyl halide can undergo SN2, but tertiary alkyl halide will not undergo SN2 because of steric repulsions. They will undergo mainly SN1 only. Primary and secondary alkyl halides can undergo SN2. And what factor decide whether they will undergo SN2 or SN1? Whether a particular
Solvent.
alkyl halide will undergo SN2 or SN1, that is decided not only based on the alkyl halide but also on the solvent, other terms. Yes or no? Secondary alkyl halides can undergo SN2 as well as SN1. When they will undergo SN2? When SN2 will undergo when we have a strong nucleophile. Whenever we have a strong nucleophile, because rate of SN2 depends upon concentration of nucleophile, SN2 is most probable. When we have a weak nucleophiles like water and alcohol and water are weak nucleophiles, there SN1 can occur. Secondary alkyl undergoes both SN1 and SN2. If you take primary alkyl halides, they want to undergo SN2 greatly because of minimum steric repulsions. Tertiary alkyl halides has a greater tendency to undergo SN1 because of more stable carbocation, whereas secondary alkyl halide will undergo SN1 and SN2. Other factors determine the mechanism. What are the other factors? Solvent, mainly solvent. Secondary alkyl halide is take when it will undergo SN2 and when it will undergo SN1. Yes or no? SN1 reaction is favored by poor nucleophile. Poor nucleophiles are only these, water and alcohol. Why? Because rate of SN1 is independent of concentration of nucleophile. Rate of SN2 is directly proportional to concentration of nucleophile. SN2 reaction rate is directly proportional to concentration of the nucleophile, whereas SN1 reaction rate is independent of concentration of nucleophile. So we have to take strong nucleophiles, then SN2 is favored. When you take weak nucleophiles, SN1 is favored. And SN1 reaction is favored in polar protic solvent, because polar protic solvents helps to ionize the bond producing carbocations. SN2 reaction is favored in polar aprotic solvent. SN2 is favored in polar aprotic solvents. Right, students, let us proceed further. Special case, allyl halide, benzyl halide, they will undergo both SN1 and SN2. As we have discussed, allyl halide, benzyl halide will undergo SN1 greatly because carbocations are more stable. They will undergo SN2 greatly because nucleophile as it attacks, it is stabilizing the carbon-carbon double bond systems. So other factors determine the mechanism. What are the other factors? Like solvent and nucleophile. Okay, whenever we have strong nucleophile and polar aprotic solvent, then SN2. Strong nucleophile plus polar aprotic solvent. Polar aprotic solvent means SN2. Weak nucleophile plus polar protic solvent. Then SN1. Okay. Benzyl and allyl will undergo both SN1 and SN2. If a particular compound undergoes both SN1 and SN2, then what are the other factors which are going to decide the type of reaction is solvent as well as nucleophile. CH3, CH2Br treated with the CH3O minus Na plus. What is the product obtained in the first case? Primary alkyl halide will undergoes SN2 greatly. SN2 means nucleophile is going to be substituting. What is the nucleophile? CH3O minus is nucleophile. In the first case, you will get what? CH3, CH2O, CH3.
Ether.
Yes or no? CH3, CH2O, CH3, which is ether. Second case, you get an alkyne. Third case, OH minus is going to attack this particular carbon. S minus attacks this particular carbon. O minus attacks this particular carbon. Same nucleophile is substituting. Cn minus attacks this particular carbon. So you get CH3, CH2O, CH3. First case, CH3, CH2, C triple bond C, CH3, non-terminal alkyne. CH3, CH2OH. This is aqueous liquid mention because in the presence of alcoholic NaOH, what happens? Alcoholic medium, elimination will occur. Elimination can occur, leading to the formation of alkene. CH3, CH2, SCH3, thioether. CH3, CH2, O, C double bond to CH3, CH3, CH2, CN. Okay, cyanates, all these compounds are produced, all these undergoing SN2 attack. SN2, 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 everywhere SN2 attack, because we have a primary alkyl halide and a strong nucleophile. Strong nucleophile there, primary alkyl halide, so SN2 will be greatly happening. Is that clear, students?
Yes, sir.
Yes.
Yes, right. Very good. CH3, CHBr, CH3, NaCN, DMSO. What type of alkyl halide is? Secondary alkyl halide. Secondary alkyl halide, what type of nucleophile you have? Cyanide. Cyanide is a weak or strong? Only two are weak nucleophiles like water and alcohol. Remaining all negatively charged nucleophiles are strong nucleophiles. DMSO, polar aprotic solvent. Secondary alkyl halide taken in strong nucleophile and polar aprotic solvent. SN2 occurs or SN1 occurs?
SN2.
SN2 occurs. Cyanide is now going to be substituted this particular carbon. That's it. Even though you do SN1, the same product is obtaining. Here, what type of alkyl halide? Benzylic. Yes or no? Benzylic alkyl halide. It can undergo SN2 or SN1. Here happens SN2 first attack. Here strong nucleophile, polar aprotic. So SN2. Cyanide and a strong nucleophile. DMSO is polar aprotic. So here also SN2. We have carbon chlorine bond, carbon iodine bond, which can be replaced. Carbon chlorine or carbon iodine.
Carbon chlorine.
Why can't carbon iodine bond? That exhibits partial double bond character in an aryl halide system. So Cn minus will attack this particular carbon, chloride leaves. Here what happens? K plus SH minus, strong nucleophile, again polar aprotic. So SN2 happens. SN2 attack occurs. SH minus will attack this particular carbon, but from the back side. So wherever we have carbon chlorine bond, the carbon chlorine, if you look at chlorine, that is towards our side, like wedge. So SH should be on the dash. If chlorine is on the wedge, SH, if leaving group is on the wedge, nucleophile should be on the dash. It is also again SN2. Secondary alkyl halides undergo SN2 reaction to produce respective products. Why SN2? Because strong nucleophile and polar aprotic solvents have been taken. Consider here what type of alkyl halide it is. Secondary alkyl halide. H2O is a polar protic solvent or polar aprotic?
Polar protic.
Polar protic, and is a weak nucleophile or strong nucleophile?
Weak nucleophile.
Weak nucleophile. Weak nucleophile polar protic means it should undergo SN1. So it becomes SN1 reaction. SN1 means what happens? Whatever the alkyl halide we have considered, that will undergo loss of bromide ion first to form a carbocation first. So what type of carbocation is this? Secondary carbocation. It will undergo 1,2 hydride shift. 1,2 hydride shift can occur to form a tertiary carbocation. This tertiary carbocation will be attacked by water. Lone pair of electrons present on oxygen, they will be attacking this particular carbon. As soon as they attack, they'll get CH3 group as it is, carbon, oxygen, new bond. Oxygen used its lone pair, so positive charge on oxygen, 2 OH bonds. Finally, loss of H plus will occur to form respective alcohol like this. It is all SN1. Okay. Hydrolysis of alkyl halide, secondary alkyl halide, if you take, that will be polar protic solvent and weak nucleophile. So it has to undergo SN1 reaction where carbocation is obtained as intermediate. So rearrangements you have to do. Ring expansion is nothing but possible because already 6-member ring is there. If solvent acts as nucleophile, then the reaction is said to be solvolysis. If the solvent is water, then that is said to be hydrolysis. If the solvent itself is acting as a nucleophile, then that reaction is said to be solvolysis. If the solvent is water, that is why this reaction is said to be hydrolysis. Hydrolysis of secondary alkyl halide proceeds through SN1 path. reaction with aqueous NaOH or aqueous KOH. What happens, students, in the first case? Aqueous means OH minus acts as a nucleophile. Alcoholic means OH minus acts as a base. So here CH3, CH2, OH is obtained, which is nothing but the major product. And OH minus is a strong nucleophile, so SN2 is happening. In the second case, you will get CH3, CH. Two chlorines or both of them will be substituted by two OH groups. Two OH groups on the same carbon unstable, so loss of water occurs. So you will get CH3, C double bond O, CH. Three chlorines are there. All the three chlorines will be substituted with three OH groups. So what happens in the final case? Loss of water happens. You get CH3, C double bond O, OH. Okay, acetic acid is obtained. In the last case, acetaldehyde. In the second case, primary alcohol in the first case. Reaction with aqueous NaOH or aqueous KOH where nucleophilic substitution has been done. Reaction of alkyl halide with NaNO2 or KNO2 and AgNO2. NaNO2 or KNO2 are ionic or covalent?
Ionic.
NaNO2 or KNO2, they are going to be ionic. They are ionic means they will produce respect to NO2 minus ion. What is NO2 minus? N double bond O minus. So now the alkyl halide, whenever you look at the electrophilic carbon is attacked by negatively charged oxygen or not? The negatively charged oxygen attack the electrophilic carbon, then the halide ion leaves. So whenever you take NaNO2 or KNO2, you get RON double bond O, that is alkyl nitride is obtained. Whenever you take AgNO2 has this type of structure, AgON double bond O. Here silver and oxygen bond is not completely cleaved. So we have the attack from the oxygen is not possible. Rather the attack is happening from the nitrogen side. So here with the presence of AgNO2 you get nitroalkanes. RNO2 nitroalkane is obtained. With the KNO2 or NaNO2 you get alkyl nitrite. With the KNO2 or NaNO2 you get alkyl nitrite. With AgNO2 you get nitroalkane. Because in AgNO2 it is actually covalent in nature. So negative charge on oxygen is not directly available because this bond is not cleaved. So attack happens from the nitrogen side. Is that clear or not?
Yes, sir.
With the KNO2 or NaNO2, since it is ionic in nature, we have NO2 minus ion, where negative charge is directly present on oxygen, that will act as a nucleophile and attack. With AgNO2, the silver oxygen bond is not cleaved. So we are not getting NO2 minus ion. So attack is not possible from the oxygen side. So lone pair of electrons from nitrogen they can attack. But there are some students who asked me earlier, so why can't the lone pair of electrons from oxygen this side attack? Why? Because nitrogen being less electronegative, it can be donating its lone pair easily. Okay. So KNO2 and NaNO2 they are ionic, whereas silver nitrate that is covalent in nature. Because of that, these reactions happen. Reaction of alkyl halide with NaCN or KCN and AgCN. Same argument again. NaCN or KCN, they are going to be ionic in nature. They produce cyanide ion Cr minus. The attack can happen from carbon side or from nitrogen side. Cyanide ion is an ion, right? The attack can still happen from carbon side or nitrogen side. But which attack is happening? From the carbon side. Why? Because the carbon-carbon bond which is going to be formed, that is more stronger. And carbon being less electronegative, it can be attacking the electrophilic carbon greatly. So cyanide ion will attack where cyanides, alkyl cyanides are obtained. AgCN if you take, AgCN means silver is connected to carbon and carbon triple bonded to nitrogen. So this silver and carbon bond that is not broken, so carbon is not free to attack. So attack happens from the nitrogen side. So you get isonitriles in the second case. Yes or no? Isonitriles or alkyl isocyanates are obtained or alkyl isonitrile. Same reason, NaCN or KCN they are ionic. If they are ionic, why the attack happens from carbon side, why not from nitrogen side? Okay. although ionic Cn minus obtain, attack happens from carbon side as carbon-carbon bond is stronger. AgCN is covalent, so carbon is not freely available, so attack only happens from nitrogen side. Is that clear, students?
Yes.
Yes, right. So then comes the next set of reactions, elimination reactions. Elimination, we have discussed two types, E1 and E2 elimination. E2 elimination, if you try to talk about E2 elimination, E2 elimination occurs in how many steps?
Single
One step.
It is similar to SN2, it occurs in single step. And what is the, how does the transition state in E2 elimination look like?
alkene.
Alkene-like transition state. So which alkyl halide will undergo E2 greatly? Tertiary, secondary, primary if you take. Tertiary alkyl halide will undergo E2 greatly, then secondary, then primary. E1 is a two-step process. First formation of carbocation, then the elimination is going to happen. Carbocations are formed. So again, tertiary greater than secondary greater than primary. So both for E1 and E2 the order is same. But for SN1 is also order same. 3 degree, then 2 degree, then 1 degree. Only for SN2 we have 1 degree greater than 2 degree greater than 2 degree. Right? But E1 and E2, how to decide whether the compound will undergo E1 or E2? Like I have a tertiary alkyl halide. Whether it will undergo E1 or E2, that is decided by the base. So strong base is required. In E2, strong base is required. In E1, weak base, because rate determining step do not include the concentration of the base. E2 elimination is anti-elimination or syn elimination? Anti-elimination. Yes or no? And E2 elimination is possible. Can it lead to both cis and trans products, or only trans is obtained?
Both products.
Both cis and trans can be obtained. We have taken some examples as well. The only condition is anti-elimination has to happen. The proton which is going to be picked up by the base and the leaving group, they has to be in opposite direction. And E2 elimination can also proceed through Hoffman's product. Like more substitute alkene is obtained, but Hoffman's product can also be obtained under some conditions. Under what conditions Hoffman's product is the major product?
And the bulky
Bulky
group is present, a poor leaving group is present, and
Yes. And
base attacking nucleophile is bulky.
third one you forgot or what?
Extended conjugation.
Extended conjugation. Okay. Whenever we have a bulky base and poor leaving group, extended conjugation, in those three cases, Hoffman's product is obtained. In the case of poor leaving group, we cannot say Hoffman's product is obtained. But what happens? What is the transition state in the case of poor leaving group, students?
Carbon ion.
Carbon ion system. Okay. All these points we are going to cover in the next class because the time is already done. The same points, whatever we have studied, the same points we are going to study with E1 and E2. After studying all E1 and E2, we will do the comparative study. Like I will take primary alkyl halide, all four are possible. SN1, SN2, E1, E2. Under what condition SN1 will occur, SN2 will occur, E1 will occur, E2 will occur. Like that, we will do the comparison between substitution and elimination because there is a possibility for both to occur. There's a possibility of elimination product, there's a possibility of substitution product. What is deciding the major product is the other conditions like solvent, strong nucleophile or strong base or temperature or not. Mainly elimination reaction is going to happen at higher temperature because it involves bond cleavages. Substitution do not require high temperature. Whenever high temperature is mentioned, you have to think of elimination. In the elimination, whenever the base is stronger base, then you have to think of E2. Weaker base, think of E1. Not high temperature, think of SN1, SN2. Strong nucleophile, SN2. Weak nucleophile, SN1. Like that, you have to proceed. Okay? Fine. Thank you all, students. Bye.
Thank you.
Thank you, sir.